So welcome back, everyone. It's my great pleasure to introduce our next speaker, Dr. Kirk Barrow. Kirk worked for a long time, or studied for a long time in Atlanta at Georgia Tech University, starting actually with a bachelor's degree in aerospace engineering, and then moved on later to simultaneously a master in aerospace engineering and studies his PhD in physics together with John Weiss. He finished his PhD in 2018, and since then he's a postdoctoral fellow at the Carvey Institute for Particle Astrophysics and Cosmology in Stanford. So it's my great pleasure, and please give the stage to Kirk. Thank you.
So I just wanted to start by thanking the great organizers of this symposium. It's been really educational, and thank you for inviting me. I'm quite honored to be here. So today I wanted to take us on a little bit of a trip away from galactic astronomy to the early universe, and I think I'm the first talk to really delve into that epoch, so I'm going to get a little bit of an overview before I dive right into what I really want to talk about, which is Nebular emission lines in H2 regions. So I'm a theorist, sorry. But ultimately, I think there are sort of two sides to astronomy and astrophysics. And the first side is in the modeling, and the other side is in the observation. And I think ideally these two sides should be talking to each other and iterating as much as possible. And when it comes to the Milky Way galaxy, we have wonderfully rich observational data, and we have a lot of great models, but when it comes to modeling a Milky Way galaxy, the entire galaxy, in order to get something like a cosmological simulation to represent something like a Milky Way, you need to really, in a cosmological context, model the entire sort of 13 billion years of the universe and all the feedback effects and all the star formation to get anything that really looks like a modern day galaxy, and that's quite difficult. So essentially, because of all of the physics that have to go into a model like that, the amount of fidelity that you get sort of goes down as a function of time when you're doing cosmological simulations, and conversely with telescopes, the further you go back into the universe, the fidelity of your observations goes down as a function of time since the present, before the present day. So from the cosmological simulation side, you have a limited amount of variables that you can sort of try to model at any point in time. I use ENSO, which is an adaptive mesh refinement, but I'm not partial to it. There are a lot of different cosmological simulation suites and software that you can use. But in addition to n-body simulations, which model dark matter, you definitely want to have gas hydrodynamics and radiative transfer. And as people who work here on the FIRE team know, how you model feedback is really extremely important to the quality of the simulations you get, especially after reionization. So in my simulations, there's always going to be adaptive ray tracing, there's going to be multi-species radiative cooling, there's going to be metal enrichment, supernova energy injection. What I don't have right now is AGN feedback and cosmic ray feedback, but I'm dealing with smaller galaxies, so it might not be important for the epochs that I'm going to talk about. So if you're a pure theorist, which I'm not, it's almost enough sometimes to just think about, okay, I have first principles physics, I have a simulation suite with a lot of heritage. I'm going to just look at the edge of what kind of physics I can put in and see if I can get a lot of new phenomena to sort of pop up in a simulation. And that's one way of doing it, and that's something that I have done. So for example, I looked at the direct collapse black hole question, and this is a question where we have quasar observations at high redshift. The quasars are of a size and of a mass would suggest that they could not have sort of accreted their mass in the amount of time that they would have had since the first stars formed. And one of the solutions to this, actually almost all the solutions, are that you have massive stars, whether they're population 3 stars or direct class black holes. But direct class black holes are really just the end phase of a sort of massive quasi-star. And the theory kind of goes, you have Lyman-Werner radiation. Lyman-Werner dissociates molecular hydrogen. And molecular hydrogen is what you need in order to quickly cool and collapse gas. And if you're not quickly cooling and collapsing the gas, it doesn't it doesn't fragment because you have sort of a uniform cooling in the gas. And it can, theoretically perhaps, collapse into a central mass, a massive star, and leave behind a massive remnant. And then the remnant starts to create the remaining gas and gives off ionizing radiation. So this is, sort of an old picture, maybe over the last 15 years, a lot of people have looked at this scenario, and this has been the picture. And when it comes to modeling observations, there's a lot of work on that. So essentially, people have used a 1D or 2D or even 3D radiative transfer models with that picture that I just showed you and gotten model spectra. Now, these objects have not been confirmed to have been observed before. So from the modeling standpoint, it's more sort of a game of making a prediction and waiting for James Webb and continuing to wait for James Webb and then making more predictions and putting in more physics and then arguing with other people about whether this even exists. But the key thing here is that it's really fine to start with first principles physics and start modeling things and making a prediction. But when it comes to making synthetic observations, you have to be very careful, because synthetic observations are usually something you're doing in post-processing. And so that means that whatever added complexity that you're using to make an actual observation or synthetic observation is not actually feeding back into the physics of the problem. And so with the DCBH question, what we did is that we added X-ray feedback to ENSO, which is not something native to ENSO. And we actually saw something completely different happen than the classic picture of direct class black holes. What we saw is that because we had ionizing radiation, and remember the Lyman-Werner radiation is what was dissociating H2. So the ionizing radiation creates a lot of sort of ionized species, protons and electrons, and what that does is it actually accelerates the production of molecular hydrogen close to the black hole, and what we saw is an immediate burst of star formation. So assuming DCBH are real, and we know that accretion of the black holes causes ionizing radiation, and there's actually a lot of work to show that this ionizing radiation can lead to the production of H2, then sort of the logical consequence of this is that you get faster cooling, and then you get a star cluster forming. And this is actually, despite sort of that chain being individually confirmed, a piece of that being individually confirmed, the fact of a DCBH-induced star cluster has not sort of been talked about before. So I really encourage you, there was a submission last week, I could talk it all on 2019, but also the paper that we submitted a year ago that talked a lot about the observational properties of such an object. And so this is the actual picture that we saw. So that accretion of the black hole has ionizing radiation, causes a starburst. These stars are forming in metal poor gas. That means that they are usually population 3 stars, they're more massive, they go supernovae. And then now you have a DCBH embedded in an H2 region, which looks quite a bit different from all of the sort of other synthetic observations that you could have you see in the literature of DCBH. And if you kind of, and this is sort of just a quick tour of my PhD and just doing theory. And if you sort of look at J-Davis-T filters and track what happens to the DCBH as it goes through the accretion cycles, you can see it takes this path in this combination of filters, and this path is sort of a completely different place where you can have color cutoffs from the galaxies. These are the metal-enriched galaxies and the metal-free halos, which you probably wouldn't be bright enough to see, but the point is that there would be some evidence just in the colors that this would be something a little bit different than what we would expect of a normal galaxy at a higher redshift. So this is at redshift 15. And Because this is a large accreting object and it has this massive star formation, we actually found that it would be visible potentially of JBST given what we put into it. But these are all predictions, right? This is a game of making, putting a lot of physics into a simulation and sort of just trusting the result and then boldly publishing a paper anyway and hoping that you got things right. And if you got things right, great, but maybe you didn't. So after my PhD, I wanted to take a look at this overlap region and take existing observations and try to sort of solve existing questions in literature in real time. But the problem with that is that this telescope overlap is not, we've looked into reionization, but if we're really going to think about the spectra of galaxies and their colors and things like that, really want lower redshift, which means that we need to run our simulations further, which means that we're going to have to make a sacrifice. And the sacrifice that I chose, because as a postdoc I don't have access to unlimited computation resources, is that instead of looking at lots of galaxies, I focus on one. So, and from that one galaxy, I created a synthetic observation pipeline. And that pipeline is completely focused on creating the thing that is the language that speaks both to cosmological simulations, observing campaigns, that is the luminosities, images, spectra, emission lines, and large sample statistics. But this isn't new. This is a field that has been sort of evolving for the last 10 years, and including in the fire simulation, which is on the left. And here's sort of my 2017 work on the right, and you can see these galaxies are different. This is something you'd expect to see in the sky, and this is a blob that has a weird shape. And the reason it has a weird shape, of course, is because this is a high redshift object. And high redshift objects have not settled into disks. They are disrupted by lots of mergers, star formation events, feedback. And because of that, a lot of the things that we sort of assume analytically don't really apply to these high redshift galaxies. One example of that is half-light radius to mass relationships. So I looked at what I call the Renaissance simulations, which is just a suite of large simulations using ENSO of reionization-era galaxies. And so here's one halo. It has lots of sort of complexes, some satellites and so forth. But what I've plotted here is blue is UV, green is optical, and red is infrared. And what these are half-light radius. So the inner circles are the minimum half-light radius depending on the viewing angle, and the larger circles are the maximum half-light radius depending on the viewing angle. And what we found is that for sort of almost all of these galaxies, because of their sort of irregular morphology, you get a big range in the half-life radius, and you can't really relate this anymore to things like their stellar population or their mass or anything like that, and you really need a different measure to look at that. We'll sort of re-emphasize that. So that Z equals 15 galaxy with a direct class black hole, it has this is column density, sort of integrated column density, depending on line of sight. It has an irregular distribution, and it isn't really until you get into the lower redshifts where the column density sort of forms a disk-like shape. And where you are, even in sort of these disk galaxies, is important. So it's actually a star-forming complex here, and you have a ionizing radiation escape fraction that sort of is really dependent on how you're looking at this galaxy. So this also sort of underlines the point that escape fraction isn't a global quantity, it's really an angle-dependent quantity, an environment-dependent quantity. And this is just to motivate that this really just takes a lot of thought and careful modeling to really turn what we see in simulations into something useful for astronomers. But here's sort of the crux of what I've been looking at more recently. So H2 regions are sort of regions of young star formation. They form of collapsing molecular clouds, as people know. But the key here, and this is giant nuclear, giant H2 region and triangulum galaxy, is that they don't look like what we see sort of in a lot of analytic models. They aren't spherical. They don't have a uniform illumination. They're very, very time dependent, and they're very sensitive to the actual local photon flux and distribution. So here's a little movie of a galaxy, and this is using a Monte Carlo ray tracing routine. But what it is that I've exaggerated the brightness a little bit, so the gas is much more reflective. But I'm going to play this. But what you're seeing here is a 10 to the 8 galaxy, solar mass galaxy. And as this galaxy is evolving in time over this 300 million year period, what you're seeing is a couple different effects. First of all, you're seeing feedback. So it's going to sort of collapse, form stars, and it's going to have supernovae, and it's going to burst out in feedback. But you're also seeing, because the star's luminosity evolves over time, some stars seem to sort of like disappear. They're just becoming dimmer over time. So most of the light you're seeing is going to come from these young stars. And to emphasize that point, we talked about this a little bit yesterday, but if you take sort of a 40 or 50 solar mass star, of course it isn't 40 or 50 times as luminous as the sun. It could be almost 1 million times or more. So it's really these young stars that are dominating the UV spectra of these galaxies. And if we want to look at nebular emission lines, so these are the emission lines that make our H2 regions, green or blue, or those red colors, or those are coming from sort of the chemistry going on inside of the H2 region itself. We need to really get a handle on an unregularized, non-homogeneous look at the flux. So we have 4 basic cases. So the most normal case that you see in the literature, this is codes like sunrise. Sometimes you see this with FSBS, you see this with Broussard-Chalot, is that you assume that there is a single source illuminating an H2 region, and then you do a chemistry and photonization calculation, and you get some emission lines out of it. You can do this at a galaxy scale or a star cluster scale. That's essentially the assumption that goes into that. So that's case 1. However, when we're looking at sort of cosmological simulations, each one of these stars is a point particle. And you can have a region that has more than one star inside of it. And the question is, how do you deal with that? How do you model the emission inside a region with more than one star particle? Or how do you get this particle to contribute to the radiation here, because it's a big particle? And how do you deal with this region here, where there's no particle in here, but you have lots of particles co-contributing to the flux? And one sort of method of doing this is to, inside a simulation, have photons going everywhere, and lots of sort of different wavelengths of photons. And I think the most I've seen at a large cosmological simulation is maybe 6 different wavelengths, and trying to get ray tracing for all of them. But I thought 6 wasn't enough, so I wanted to do 8,000. And I wanted to do that because I wanted to actually capture little fine effects that happen that really matter when you're thinking about one ionization state of a species over another one. So if you want to look at O3 to O2, or if you want to look at helium-2, it's really important what's happening to the mean ionizing photon of those species. So the first thing I did is looked at absorption. So you create a model for absorption that is dependent on temperature, density, the photon at background, because that tells you what species that you have. And you look at those case 2, case 3, case 4, and what you see, so green is unattenuated, blue is attenuated, and red is the internal spectra. So when you have multiple interior sources, the ionizing radiation is dominated by The interior sources, if you have only exterior sources, some of that ionizing radiation, or most of it, is attenuated. And if you have some arbitrary illumination, you get some mix of this. But it's important to distinguish between these cases. So that work, that sort of recent work that used those 6-photon wavelengths in order to get emission lines, what they did is that, so they looked at all of these infrared lines, and I'll tell you why they're infrared in a moment. But what they did is that they had sort of all those variables: metallicity, density, temperature, and these 6-photon backgrounds, and they created a grid. And if you just do the math on that, the grid was several million different possibilities. And then that became sort of too many Cloudy calculations to do. So Cloudy is a coordination software that a lot of people use. So what they did, instead of calculating for a million, and there was a million cells in the galaxy too, so there was really no way to get around there being millions of Cloudy calculations that had to be done, is that they did machine learning algorithm to try to predict what the emission lines would be based on a training set. And this was found to be pretty good for infrared lines, but for UV lines, this would be off by 20–30%. And each one of the cells in their simulation would always have sort of a constant illumination, which is not really good if you're thinking about that H2 region. So the H2 region is going to have different amount of illumination if you're on one corner of it versus the other, and that's really important. So what I looked at, and so by the way, I'm using pronouns like I and we. So when I say I, it's because unfortunately I have a single author paper out there. Don't do that until not in your first year of your postdoc, but but I'm trying not to take credit for anything that I haven't done, and we'll see what the reviewers think of that work. But what I did is that I did a lot of work to try to model the exact flux distribution inside the galaxy, so that I could get the fine details of the H2 region in sort of a subgrid scale. So the solid line here is the actual flux. If you just go ahead and ray trace to trillions of points in a cell, and you sort of look at the cumulative volume fraction and what is the flux. This dot dash is my model, and I've created sort of this analytic model. I decided a long time ago not to put any equations into presentations. So there's a paper, you can look at the model. But this dashed line is what happens when you assume that each cell is an independent system. So that's a lot like Broussard-Chalot or Sunrise. And what I found is that if you don't model flux from every source and you don't ray trace from every source, what happens is that you have orders of magnitude discrepancy in the flux distribution. That means that your photoionization calculations are way off. Versus here, and this is actually one of my worst cases, I've improved it since I've made this figure, but what I can get this is down to something like 5–10% of the true flux. So this is just the error between the dot dash and the line, but I can get it down to 5–6–7% between my model and the true flux distribution if you do a lot of heavy work. But of course, what it means that I have a model is that it's analytic in a sense that it allows me to do this without running a million Cloudy calculations. So what I've done is that I've done attenuation and I've done flux matching. So what is the scientific question? Why have I done all this work? So it turns out there's a lot of mysteries about the nebular emission lines, and there's a lot of mysteries because modeling nebular emission lines is quite a recent undertaking. I would say maybe the last 5 or 6 years people have gotten pretty serious about it, and only in the last few years have people really started putting out a lot of predictions for high redshift nebular emission lines. So here's a Shirazi 2012 observational paper, and this is the HE2 to H beta ratio. Now, I named my presentation Blue Galaxies, and the reason I named it Blue Galaxies is because both helium-2 and H beta are blue. They give off a blue color. And the ratio between the two of them usually tells you something about the temperature of stars and the number of ionizing photons. So the more ionizing photons you have, the thought is that you get more He2. And the ratio between the two of them in an H2 region can be something like 2% or so. So 2%, so 0.02 He2 to H beta. But anything more than a percent on a galaxy scale is anomalous. So what I'm showing in the Shirazi paper is that, so there's a model, this is using PyNeb and a lot of sort of established software, where the predictions are underestimating the observed ratios by up to an order of magnitude systematically. And there's a lot of research and literature to try to figure this out. This has been a mystery since the 90s. And the first thought was, okay, maybe these are Wolf-Rayet stars, or Wolf-Rayet galaxies, a galaxy dominated by Wolf-Rayet emission, and those are stars that have a lot of hard ionizing photons. There was thoughts about this was due to AGN, and it's true that there is an AGN population amongst these, but these are sort of really easy to distinguish with the BPT diagram from the star-forming galaxies, and the star-forming galaxies also had high ratios. There's thoughts of shocks, and then when that wasn't enough, people started to think about, better modeling binary stars or stellar winds. There was a lot of work to try to figure out how to fix this discrepancy. And I thought it would be cool to see what happens when you take my flux modeling and my attenuation modeling and see what is the discrepancy when you go through all of that radiator transfer work. Some more recent work, just showing a few more observations and showing the range of H2 to H beta, as well as line ratio diagrams to show that a lot of these different explanations occupy a really sort of unique space. So even if you look only at the star-forming galaxies, there's still really high ratios. So these blue points here are still, they're in the star-forming complex, and they're not sort of explainable by these other mechanisms. So that movie that I showed you of my simulated galaxy, at each one of those frames, I did a photonization calculation throughout the galaxy, and this is what I found for the He2 to H beta ratio. So because of the feedback, you saw it was a bursty star formation, and what I found is that I do get quasi-periodic jumps in the ratio up into the regime that you see in observations. But this is just the ratio, and what you see right before, and this doesn't really explain it, so what you see right before each one of these peaks is a minimum. And the reason you see a minimum before a peak is because this is a ratio, and it means that something's happening to H beta right before something happens to He2. And it's exactly what I saw. So this is getting hard to look at, but you have this is star formation here. You have a jump in star formation, and then that causes a jump in the galaxy-wide H beta. And a little bit after that, about 5 million years after that, you see the jump in He2. And H beta sort of decays over time since the last burst of star formation. And if you can time that right, if you have enough time between these bursts, what happens is it decays enough that the ratios becomes high. You get these 2, 3%, 4% ratios. So the kind of tentative answer to the question is that this is really just a function of a time-dependent model for these line ratios. So maybe this is just due to waiting enough time between star formation for H beta to go down to get these high ratios. But that last plot, really it only has one data point for every one of these peaks. It doesn't really tell you too much. So one of the things I sort of figured out when I was running these simulations is that you need a lot of temporal resolution to really look at these patterns. So if you take sort of every 19 million years, you get a random phase because these star-forming regions really only emit this strong ionism radiation for periods of up to 20 million years. So you really need to dig down in these cosmological simulations to these really small timescales. So here I'm using timescale of about 400,000 years per time step. And that allows me to see that, okay, these bursts actually last for 1.5 million years or so. And drilling down into sort of the volumes of gas that are commensurate with these high ratios, I saw some further trends and sort of started to explain why this was happening. I'm trying to figure out the best way to present this, this information, but what I've done here is that it goes from light to dark as time goes by, and here's a spectra, so the lightest spectra is the earliest time, and the darkest spectra is the latest time, but what I want to emphasize here is that in this medium time, it has the hardest spectra, and this is because of the Wolf rate phase. So after some delay from the onset of star formation, you go through the Wolf rate phase of the mass of stars, and that is the thing that triggers the He2 formation. And it isn't correlated specifically to things like the ionization parameter. So this isn't the highest point in the ionization parameter. That would be over here. And it isn't correlated specifically to the star formation rate. In fact, because of the effect that I just talked about, that you actually need a little bit of time for the H beta to cool down, a high star formation rate actually implies that you have higher H beta and a lower ratio. So here's the correlation sort of shown. So the mean ionizing photon is strongly correlated to the He to H beta ratio. So this is really just a function of the hardness of the spectra. And the ionization parameter isn't correlated at all, which is just sort of important to think about for people who are trying to model this. Because I guess I should add that that was really what people were thinking was the solution, is that this was due to the ionization parameter. I was sort of combining the model of observations. What I did here is, so I'll start with the right. This is the BPT diagram with the same observations. These are in blue. The observations from the 2017 paper are these triangles here, and then the squares are from my simulation. Now, one flaw, or something I need to overcome in the simulations, is that my simulations are redshift 4.5, which means, and these are smaller galaxies, so my metallicity is quite low. And there's a metallicity relationship with these lines. And so what I did is that I took a region inside that is producing a lot of this radiation, and I just changed the metallicity to see what the evolutionary path is. And all of these would sort of go into these observations. There is one that is a coincident observation, but all of these sort of take a path like this as metallicity goes up because, for example, the nitrogen abundance increases. And so there's 2 points over here that are beyond the AGN line. And this is, again, 3 regions inside my galaxy, and what happens if you evolve the metallicity to values that are nearer to solar. And what I find is that all of the observations, except those 2, which are above the AGN line, are within the model for what I see inside my galaxies. So I call it a solution. It isn't really a solution, but it is sort of one of the, it's a preliminary model that takes that order of magnitude discrepancy in predictions observations and sort of starts to address it. So these are almost all the observations of He2 to H beta at high redshift. So these are from redshifts 2 to 4. And it seems, at least tentatively, that you can model this if you're really careful about the radiative transfer. There's lots of other line ratios that are a quandary. So for example, O3 to O2, this is from a very recent paper. This is from last month. And so these are the observations. And looking at that same short period in the simulation, this is what I get. And noting here that these are all galaxies, and this is a single galaxy exploring the same parameter space. And the reason that happens is because to put it very simply, the O2 decay is kind of like the H beta decays. Faster, the O3 starts a lot higher. So each one of these, this is colored again by time. So each time that we have a starburst, it kind of jumps up here and then goes back and jumps up and goes back, and you get this cyclic pattern that explores the same parameter space. All right, so I'm going to quickly conclude because I think I underestimated the time, but so I actually talked about a few different things. The first is that DCBHs, from a theoretical standpoint, if they exist, might trigger star formation, and that changes what we might expect from them in terms of observations. So this is and I showed a few of the first models of H2 regions on a cosmological scale and a galaxy scale that really looked at attenuation and flux matching and photonization of arbitrary distributions of sources within the galaxy. And what I found is that the H to the H beta ratios are explained by hard ionizing spectra. And if you have a star formation history with 15 megayear gaps in star formation, you get these high ratios. So that's one hint as to what might be causing these high ratios. And the O3 O2 emission line trends are explainable by the differential decay rates between O3 and O2 lines. So that's what I have. Thank you very much. I'd be happy to answer any questions.
I really like your time-dependent explanation and solution to the helium-2 excessive strength. There's another effect that might be something you might consider. So a couple of decades ago, I was working on a high-latitude planetary nebula in which helium-2 4686 was almost as strong as H beta. And it was very high excitation. You could see neon 5. It wasn't overabundant in helium. And what we finally concluded, the way to get that was essentially it was mass limited inside the helium plus zone. So if you have, in addition to time-dependent effects, maybe you have directional dependent effects. In some direction, you run out of mass, and the radiation escapes to some large distance or something where you don't see it, or it's by then the ionization parameter locally is very low. So distribution of gas geometry. So now you need high angular spatial resolution in addition to temporal resolution.
Right. So, I kind of rushed through that. It was something I considered talking about as I was going through the slide. So off this slide, way up here in the 25% range, there are more points, and the reason is exactly what you talked about. So these are points where you've actually saturated the gas. So this is low density gas where you have a lot of escape of ionizing radiation, and that causes a really high ratio. But the thing is, on a galactic scale, because it's a low density gas, the actual luminosity coming from those regions is low. So those regions didn't contribute to the galactic scale ratio as much as the regions that are plotted here. But you're right, that is, you can have almost arbitrarily high ratios in that case.
So given the computational expense for your radiative tracing and the temporal resolution, so how tractable is this problem in more in larger scale redshift 0 cosmological simulations?
So it is tractable. So I will say that doing all of these sort of post-processing, including, the simulation and all the post-processing and all the things for this 10 to the 8 solar mass galaxy in stars, it took about 3 weeks to get the data set. So the way that I've done the ray tracing and everything, it's probably about, if you take 100 cores, you do one time step of one galaxy in about 3 hours. Yeah. I mean, a lot of people have hundreds of millions of core hours, so, but yeah, so actually I'll put it that way. So I don't have a large allocation. I should have done this during my talk. All of this is done at Tech. Thank you very much. But I don't have a large allocation. I have maybe 12,000 node hours in STEMP2, and all of this work I did it in like 3,000 or 4,000 node hours. Mm-hmm.
That's all post-processing, right? Are you talking about doing the simulations as well?
Yeah, the simulations as well. Mm-hmm. Yeah, everything is parallelized, every single step, or it wouldn't work.
So on the simulation side, now that you know all these things that you've learned by thinking more carefully about how to represent the emission properties, including post-processing, ray tracing, and so on. If you now were to go back to the fundamental simulation, what do you think these uncertainties are that remain there that you wish you could, by kind of iteratively or self-consistently take account of?
Yes. So I think the next step for this, and this is something else that I could have mentioned. I've gone really excessively into, so the AMR level that I'm using corresponds to a resolution of like 2.6 parsecs. And I found that really, so that's a good resolution, by the way. But I found that resolution was important because when I have a starburst, it isn't a single particle. It's usually lots of particles. You saw it was integrated over time. And I thought that was important because each one of these particles is a different sort of phase, and that allows it to disperse over time. And it allows us to have these sort of non-spherical H2 regions. So I think it's really important to have star clusters dispersing, especially early on, because that really affects how much flux is getting into the gas. But I think that's within our power to do now. In terms of feedback, I think it's important to really get the ionization state of the multi-phase gas self-consistently inside a simulation. And that allows you to do the absorption very well, especially with metals and dust. So I think that having multi-phase ISM and a few more photons to try to track those ionization states within a simulation will be important to actually getting a better handle on the evolution lines, which gets you a better handle on what's going on physically from observations.
Is there a last question? I think we're almost at 1:30. So thanks a lot, Kirk, for this very nice session.
Thank you.